Recorded is rolling. It is Tuesday, October 25th. All right, so yesterday we started a new topic, energy. Also, your centrifugal force and gravity quiz. Please do. Most of you guys turned in, but hadn't yet. Please do get that in, so I can grade those and give those back to you guys. We turned it yesterday. It's already in focus. And so I've got some demos lined up for you guys. I'm going to add to the notes a bit, and then this table that we started on yesterday. We're going to get to this, but we might only have time for one or two of these by the end of class because there's some other stuff I want to tell you guys. Okay. Yeah, and then part of the story I'm going to take for tomorrow too, the whole escape speed part of the story. Get a lot to you guys by this Thursday, and then of course we kind of got a 4-day wait because laptop day is Friday. All right, so I'll really link through yesterday's notes because we started a whole new topic, whole new framework, way to think about things. We got this new variable energy that we're quantifying in joules. Now, there are other ways to also measure energy, but I'll talk about that later today. Okay? But this is the main one that we care about. 1 joule breaks down into these SI units. And interestingly, it is conserved in the universe. Like you can't create or destroy energy. So if you have a closed system where energy is not entering or leaving, then the quantity of this in that system is always the same. And you can use that to solve problems. Like here's what it looks like in like physics math type form. Right? The sum of energy initial equals the sum of energy final within some closed system. Okay? Now, what are those energy types? I'm saying sum of, like maybe you're adding up different energy bits. Okay? Now, when we're setting up problems and solving them in this class, these are like these building blocks that we're working with. Right? These types. Right? These are forms of mechanical energy. Energy takes other forms too. Like I don't have thermal energy on here. I don't have like chemical energy, but those could be types, right? Now, if you have an open system, you might start with some energy in the system. You could add or subtract the work that's being done on or by the system, and then end up with final energy, some version of that. Okay. So these forms of mechanical energy, like these building blocks that we're interested with in this class. So work is like a transfer of energy. This could be force times distance. This is a dot product, meaning that you're only multiplying together the parallel components. Okay. So let's look at some examples here. Suppose you lift an object, like lift a textbook. Well, I have to apply a lifting force at least equal to the weight of the object. In fact, if it is the same force, I might be moving up at constant speed, right? Constant velocity. Okay? And if I am applying an upward force and I'm also moving it upward, well, those are definitely parallel to each other. So I can just multiply that force and that distance. Boom. I did that much work lifting the book. Okay? Whether that came from my muscles or if I had to break it up to some mechanism, right? 30 joules had to come from somewhere lifting the book. Okay? Now hold on to that idea because a couple of pages from now, that's going to also represent the potential energy of that book. That's where the energy had to go. But save that because let's look at a couple other examples with moving this book around. Suppose you move the book to the side, right? Like horizontally across the room. Well, in this case, your applied force, like this lifting force, has nothing to do with the lateral motion of the book. Right? These guys are completely independent of each other because they're perpendicular. So there's no, like this force is not doing any work on the book if it's not lifting it. The book is only moving horizontally. Okay? If you want to see that more mathematically, the angle between these two is 90 degrees. So cosine of 90 degrees is just 0. So there's spelled out a bit more specifically. Okay? And what about like pushing on some angle? Okay? Here's where like the cosine versus formula is particularly helpful. Right? So what if I'm pushing a grocery cart with 50 newtons of force, but kind of down on this 37-degree angle below the horizontal, and the grocery cart, of course, only moves horizontally. Right? Well, 37 degrees is really nice because it says to put 3, 4, 5 right triangle, because I want you guys to see the big picture of this, which is that only this component is actually pushing the cart forward in the forward direction. Right? And since this is a 3, 4, 5 triangle, this is 4/5 of this, 4/5 of 50 newtons, is 40 newtons. So 40 newtons multiplied by the distance that the cart is pushed tells you the work that was transferred into the cart, pushing the cart forward. Okay. Now, that could do one of a couple of things to the cart. It might be speeding up the cart. That's to say, translating into kinetic energy, right? Energy motion, right? Or what's also possible is maybe the friction force is taking energy out of the system. So maybe the friction force times the distance moved could subtract off 280 joules so that the cart's just moving at constant speed. There could be something like that going on. Okay. Let's go back to like lifting this textbook though. Right? So when you lift the textbook, it takes some work to lift it. Right? And you've essentially transferred that energy into the book and what's called gravitational potential energy. Right? So here's it comes straight from the formula of work lifting the book, because here's the force you have to apply to lift the book, its own weight. And here's the distance you lift the book called height. Put it all together, mgh. Right? Work done lifting the book, potential energy goes into the book. Right? And you can get that all back if you tip the book off the shelf. You're like, tip, it goes through, crashes on the floor. Right? So the more massive the book, the more the gravity field of the planet, or the higher you put it on the shelf, is all going to result in a bigger crash. Right? Now I'm saying this is localized to the surface of Earth because that lowercase g is only true at the surface of Earth. Right? Tomorrow, I'll fill you guys in on what happens if you like blast a rocket off to the moon and that g significantly changes. Right? So we'll worry about that in the future. Right? So not today though. Right? And so force times distance, lifting a book, also called weight times height. Right? Here's what this looks like on the graph. Right? Force, height. Right? It would be like a rectangle type graph because it would be a constant force. Right? So the area the area of that rectangle represents the work you put into the book, lifting at the potential energy you give the book. Right? Which is a perfect segue for talking about springs, which is the same concept, but it's a different looking graph. Because remember, a spring, like the more you compress a spring, the more force it takes. So that's a direct relationship that's called Hooke's law. You guys remember that? Okay. Or if you're not compressing a spring, like I'm doing right here, I'm compressing the spring in my pen, okay, you might be stretching the spring like you do with your spring tails for your lab. Right. However you do it, the slope of this is the spring constant, how stiff is the spring, and the area underneath the curve represents some number of joules. It's still newtons times meters, okay? But it increases more and more the more you compress the stretch of the spring. It ends up being 1/2 kx squared, where k is the spring constant of the spring. Okay? And finally, energy of motion, called kinetic energy. We can quantify it like this: 1/2 mv squared. Maybe this graph is a justification, possibly. Got an example problem here. All right, so that was yesterday's stuff. So let's switch over to today. Here, I've got some demos for you guys. Got some video demos. So I'm gonna switch my screen over. Right, and pull up. Right, let's start with how about this guy?
Everybody knows about playing with dominoes, but what you may not know is that a domino can knock over another domino, which is about 1.5 times larger. So what I have here is a chain of dominoes. Each one is 1.5 times larger than the previous one. And the smallest domino is about 5 millimeters high and 1 millimeter thick. And I will carefully place it. And there are 13 dominoes. And the largest domino, it weighs about 100 pounds and is more than 1 meter tall. Ready? Boom. That was 13 dominoes. If I had 29 dominoes, the last domino would be as tall as the Empire State Building. Here we go. What's the physics going on here? Well, every time you stand up a domino, you lift it against gravity, and that stores some of gravitational potential energy in the domino. And you only have to put a little bit of push to get it to that tipping point, and then you get all that energy back again when it falls over. And that's more than enough energy to knock over the next domino, which releases even more energy. So it turns out the amplification in this series of 13 dominoes is about 2 billion. So we put in a little tiny bit of energy at the beginning, and we get 2 billion times as much out at the end.
All right. I'm going to switch back over here real soon, but just if you want to see it, because some of my students requested earlier to see it this. Okay, so here's the domino laying on its side. Its center of mass is really close to the ground, right? Then you lift it, take some effort to lift it, right? You're putting some work into it, and you're giving it some potential energy, where this H is the difference between where its center of mass was down here, close to the floor, and where it is like standing up. Okay. There you go. So there's potential energy. Okay. And so let's switch back over and we'll do a couple more. Let's bring up Paul Hewitt time. Paul Hewitt.
Let's suppose we have the case of a person up at the top of a flagpole. And they're up at the top of that flagpole, and they're going to dive into a little bucket of water. They used to do this in circuses, okay? And here's a dude up here. He's going to jump. And let's suppose up at the top there, he has 10,000 units of energy. That's his potential energy, isn't it? He's at rest. So being at rest, what would his kinetic energy be? 0. Just say 0. And right into the bucket. When he gets down to the bottom of the bucket, the potential energy is what? 0. Because we took this with respect to the ground. So down here, it's got a potential energy of 0. I know you're sitting next to someone knows what the kinetic energy of splat is. I know you do though. Just double check to be sure. What's the value of the kinetic energy here? How much kinetic energy? How many people don't say 10,000? Go on, you guys. It's gonna be 10,000. 10,000 units. Hey, when the dude gets halfway down, the potential energy is only half. 5,000. There are people can calculate what the kinetic energy must be. See if you're sitting next to one. What's it going to be, gang? 5,000. Let's suppose when he gets 3/4 of the way down, his potential energy over here is now only what? 1/4 of this, 1/4 of that. Looks like 2,500. Will the kinetic energy be more or less? You know it's going to be more. Picking up, huh? And what will the kinetic energy be at the 1/4 up mountain? A, huh? 75. Such that what? Do you see the rule here? Here, 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 anywhere. Going to have the same energy. And when he finally comes down here, the kinetic energy goes to 0. Boom. Calculate the heat of the bucket and the heat of his remains. And what do you got? Then you've got 10,000 units of heat energy. And that dissipates. But it's always there. Energy score stays the same.
So the extra step we're going to take it is, say if you know so many units of kinetic energy, you can set that equal to the expression 1/2 mv squared, and you can solve for stuff like how fast does he go on like 3/4 of the way down, something like that. All right, one more. Got pendulum.
Been brushing and flossing your teeth, keeping them nice and healthy, huh? Not going to do much good if this 14-pound ball comes crashing through them, yeah? Watch this. I want to show you a nice physics demo. The ball doesn't smash my teeth. How come? How come? Because of a very important conservation principle called conservation of energy in physics, which states this. Take some energy to lift the ball, yeah? Now it has energy of position. Call that potential energy. I let go, it turns into energy of motion, kinetic, back to potential, kinetic, motion, but no more potential energy afterwards than that which I start with. Try this sometime. Give the ball a little push. You better move your head. You know why? Because you gave it some energy in addition to the potential energy, and it will come higher.
All right. So switch back over here. And I want to elaborate on his example with the pendulum. So let's do that. Let's get a closer look at that pendulum. So maybe the pendulum started hanging just like straight down. Okay. Oh. And then you swing this thing up, swing up to like right here at some point. Like this. Okay, so here's the mass, the far end. Okay. This is some mass M. Okay, then it swings down. Okay, you guys can see it swinging back and forth, right? Okay. At some point, it's down here. Okay, same mass, right? So up here it has all what kind of energy again? Potential, and at the bottom it has all kinetic. Right? It has some speed down here, right? In fact, it's 100% kinetic as long as you define this line right here as height 0, right? Which is probably the easiest thing to do. Now, if you define height 0 as like down here at the floor and say it has a mix of potential and kinetic, right? You could still set up the same equations and it will setup would look a little different, but you could still look at the exact same speed at the bottom here. Okay, and that's gonna be the question: is I wonder how fast this is moving here. Okay, maybe as a function of what is the length of this pendulum. I think it's a solid line. Okay, let's call this like L for length. Right, and how about the angle that you pull it up to? This angle theta. Right. Do you think that how fast it swings through might also have something to do with here, how about this? What if I take this whole system to the moon? Because on Earth it might look like this. But on the moon, do you think it's like? So do you think that the gravity field also matters? Right, G? Right. All right, so it's that combination of variables could somehow determine like how fast it's swinging at the bottom. Okay, and I think when I pull this up to the place where it's all potential energy, okay, that there's been a height change. Okay? So to look at these two elevations, you guys see clearly a height difference. Okay? I'll call that H for a height difference, right? Okay. Right, so you guys know at this point it's 100% potential energy, that's U sub G, and at this point down here it's 100% kinetic energy, so capital K for kinetic energy, right? Okay. And I'm defining height 0 meters at this bottom dash line, right? Is that okay? That's up. Okay. All right, now let's set up an energy conservation and go solve this thing. So I'll say the sum of energy initial, I'll call this point A and point B. How about that? Sum of energy at point A is equal to the sum of energy at point B. Okay. Now I'm saying sum of energy because there could be different energy bits, like you gave this thing a push or something, but you did, you just released it from rest. So very simply, it's all mgh at point A, and it's all 1/2 mv squared at point B. I'll put a little subscript B on that B. Right. Now let's say that's what we're solving for. Right? Is that true? Okay. Now, hey, does this look exactly the same as the setup we did yesterday for Galileo dropping the ball at the Leaning Tower? Right? We did this already. We said that is equal to that, and we already solved this. It's square root 2gh, which is again something you guys solved many weeks ago. Square root 2gh, just from a different method. The math cancels out. Boom, boom. Okay. So here, I'll just cut straight to the answer because we already solved this. It's a square root of 2gh. Okay. But I'm going to add one last detail, which is particularly interesting for this this pendulum, which is this h is really a function of how long is the pendulum and what angle did you pull it up at, right? So we're going to spend a couple minutes here figuring this out. Okay. What is this h as a function of this L and this theta? Okay. I'll do this both in terms of variables, but also I'll break out some, here we go. Some peaking, and then I'll give you guys some numerical examples. Okay, so do you guys see the length of the pendulum here? Here's one of the really good things you can get out of the class like this, physics, is seeing something that initially looks complicated, but then just breaking it down into smaller parts, saying, okay, like I can see this big system. I see that this L is equal to this L. Okay, I see that this H is the difference between this L and this side of this right triangle. Hey, you guys see a right triangle? We're about to have some trigonometry kick in, aren't we? Okay. Can you guys solve for the leg of this right triangle? In terms of, say, you very easily measure this angle, or sorry, this length of this pendulum, and also this angle of the protractor, right? Yeah. Guys, is this L times cosine theta? Right? L cosine theta. So I'll call this L cosine theta. Right. I'll do this in terms of variables first, but I'll put some numbers in later. So wouldn't H just be the difference between the full length L and L cosine theta? Would that be true? And if you want to be fancy about it, I guess you could factor out an L and call it L times 1 minus cosine theta. You guys can do that? Okay. So where that H is, I'm going to do that. You can say the speed at point B is the square root of 2g, but instead of H, I'm going to say L times 1 minus cosine theta. Okay. Right, there you go. So now you can solve how fast is the pendulum going right at the bottom. For a pendulum of any length pulled back at any angle. In fact, you could even change planets if you wanted to. Right? Now that's a general answer in terms of variables. Okay. Hopefully you guys can follow that. But if you want to see a numerical example, let's do that. I'm going to call this length. Break out the pinking. Okay. Let's call this length equal to 10 meters. Okay. Nice round number. Now let's call this angle 36.9 degrees. Okay. You guys know there's a reason I'm picking that angle, right? Okay. Because when I pick that angle, I'm setting up a what triangle? 3, 4, 5. Okay. Now, of course, I could have picked any angle, and you guys get the answer. But this is a very nice ratio, because isn't this like a 4 to 5 ratio? You guys, what is 4/5 of 10 meters? 8 meters. And if this whole pendulum again is 10 meters long, and this is 8 meters, then what's the height change? 2 meters. You guys see 2 meters, right? Okay, so boom, boom, just that fast. You guys see that? Okay. Right, so let's pop this in. Let's see, what is the speed at point B? Right, notice I'm saying speed and not velocity, because using this method, energy is a scalar value, so you lose direction information. So you got square root of 2 times, we'll pop in 10 meters per second squared. Let's go say G equals 10 meters per second squared, we're going to put this on Earth. Okay. And then this whole bracketed stuff, which really represents H, you guys see very simply is just 2 meters. 2 meters. Okay, is that okay? Just like that. Okay. So, there we go. What is the square root of 40 bunch of units? Okay. I'm looking at 6.3 about, that'd be meters per second. So there you go. Okay. Now that's of course is for this particular length and angle, right? But in general, you could do something like this. All right, you guys good there? Okay. All right. All right, so moving on in the notes. Next concept I have to tell you guys about, couldn't get to in the notes yesterday, is power. Okay, so power is a rate of work, or you could say a rate of energy. Rate of energy. Okay, to give it a more mathy looking setup, okay, you could say power, and the symbol for that is going to be capital P. Okay, is equal to work per time or energy per time. Okay, so hey, maybe there's like an appliance that pulls like so many watts, right? Could you guys quantify this in watts? Quantify power in watts. Okay, capital W. Okay. Like there's some rate that's pulling energy off the grid. How about like a light bulb, like so many watts on a light bulb, right? Or maybe there's like a power plant producing like so many megawatts or gigawatts. Right? Okay. So because it's a continuous thing, right? Like continuous energy usage. Okay. Now that capital W right there, you guys saw a capital W yesterday to represent work, like as a variable, but this capital W represents watts as a unit, right? So in physics, when you see capital W, be careful. You have to be careful about the context, because it might say like W equals 3J, in which case, you say, oh, the work is equal to 3 joules. Or you might be saying something like P equals 3W, which means like, oh, the power is equal to 3 watts. Right? You guys get the idea? Right? And you can see what 1 watt is. Let's link it back to base SI units. You can get it from this formula right here. Right? So 1 watt is equal to 1 joule per 1 second, 1 joule per second. Okay. And that's going to break down into 1 watt is, see, joules is newtons times meters, and that breaks down further. So at the end of the day, this is being this 1 watt is the same thing as 1 kilogram meter squared per second cubed. Okay. There you go. There's 1 watt. Okay. So draw my light bulb example. Suppose you look at a light bulb. And on the light bulb, it says like 40 watts, 40 watts, right? That means if you have this thing plugged in and turned on, it's drawing 40 joules per second off the electric grid. Or if it's a flashlight, maybe 40 joules per second out of the battery, right? Now, of course, that energy isn't disappearing. It's just being converted into other forms. Right? So maybe it's going from like electrical energy into like light and heat, right? Which we're not going to super much get into this semester anyway, but you can quantify it, you can keep track of it in joules. But let's do an example with power. So example, let's have a motor lifting an elevator. All right, motor lifting an elevator. Okay, so draw this out here. All right, got an elevator. Oh, so it's got cable up the elevator shaft, and at the top, maybe there's like a motor, it's like pulling the elevator up. So this elevator has some weight. Let me give you guys a weight of, how about 1,000 newtons? Nice, even 1,000 newtons. So if I'm pulling the elevator up at constant velocity, then I bet the pulling force is also 1,000 newtons, right? And let's say that I pull this elevator up a height of 50 meters. So H is equal to 50 meters, height 50 meters. Okay. And this all happens in a time of 20 seconds. Okay. Remember yesterday, I never said anything about time, right? But now I'm bringing time back, right? Because that's going to help us answer one of these questions. Okay. I have two questions. One is how much work was done lifting the elevator? Like how much energy did it pull off the grid? Okay. But the second question is going to be how much power, that which involves this this time interval. Okay. So first question first. Okay. How much work was done lifting the elevator? Okay. Well, we got work is equal to force dot distance. Okay. The force is 1,000 newtons. The height is 50 meters. Put it all together, getting 50,000 joules. You could also call that like 50 kilojoules. Right? Wouldn't that be true? Same thing. Right. Follow-up question: how much power was done by the motor? And so, what rate is the motor pulling energy off the grid? Right. What is it rated at? How many watts? Right. Well, we could go power is equal to work per unit time, right? So rate of work, right? Work per time. Okay. So we're gonna take those 50,000 joules and say this all happened in a 20-second time interval. That's like 2,500 watts. Or if you like, you could even call that 2.5 kilowatts. Okay. So 2,500 watts. Hey, isn't a really bright bulb like 100 watts? Could you say? Especially back in the day, these old incandescent bulbs might be 100 watts. So if you have like 25 of those 100-watt light bulbs, that'd be pulling say an equivalent power to what this motor is pulling this elevator up. Right, you guys get that? All right. I want to give you guys another sort of a sneaky formula for our power, which might pop up in one of your homework questions. Okay. So let's go back and look at the formula for power, which is work per time. Okay. But work, hey, isn't work force times distance? Right, and then T per time, right? Okay. Now you could, if you want to, say force times distance, call that work, divide by time. You could solve it that way. Say, okay, we did that much work and that much time, and solve it that way. Right? But do you guys see you could rearrange these variables a little bit differently? What is that right there? What is distance per unit time? What's that called? Speed, right? Miles per hour, meters per second, speed. Can I say that power, so capital P power, is equal to force times velocity? Can I do that? Okay. I think I can do that. Okay. Let's see if this actually works. Okay. So P is power, right? Let's use the exact same numbers we just used. Okay. Like if I move the elevator up 50 meters in 20 seconds, couldn't the speed just be 50 meters in 20 seconds is equal to like 2.5 meters per second? That'd be the speed. Okay. Let's plug that into there. And then the force is same as before, 1,000 newtons. Okay. So let's say power is equal to 1,000 Newton pulling force, 2.5 meters per second. Okay. That gives me what, 2,500 watts. Okay. Oh, that's the same thing we got before. 2,500 watts. 2,500 watts, right? It's a different path through the force, but sometimes this is pretty useful, right? If you know a constant force you're pulling at, and you know the speed you're pulling at, it's like a constant speed. Yeah, just multiply them together. Okay, you guys good? All right. Let me get to something I've been promised you guys that I've been telling you about, but now's a good time. Right. Ways to quantify energy. Okay. Because I wanted to wait to tell you guys about power before I told you guys ways to quantify energy, because one of them goes through power. Okay. Now, of course, you guys know joules. 1 joule is equivalent to 1 kilogram meters squared per second squared. Okay, so you guys know that one from yesterday. But suppose one day you guys have to pay a utility bill at the end of the month, right? You've been using some power, you get a utility bill. Okay. The utility company is probably not going to say you use so many joules of energy. They're probably going to say you use so many what? kilowatt hours, right? Kilowatt hours, right? So what is 1 kilowatt hour? Right? Now I do want you guys to see that this is a unit for energy. It's a weird unit. I don't know how this convention got stuck around, but right. But here, watts is energy per unit time. Hours represents a unit of time. Hey, energy per time multiplied by time. That could represent a quantity of energy, couldn't it? Like watt hours. And kilo just multiplies by 1,000. Right? So thousands of watt hours, right? Now it's weird, yeah, combination of units, but I'm curious to know how many joules is this equivalent to? You know what this calls for? Dimensional analysis. Dimensional analysis. Right. So maybe different ways you can set this table, but let's do one way. Okay. So I know that 1 kilowatt is equal to 1,000 joules per second. Right. So 1 kilowatt is equal to 1,000 joules per second. Okay. And I know that 1 hour is equal to 3,600 seconds, or you could do 60 seconds in a minute, 60 minutes in an hour, but we'll apply to that. So the only unit left on the board is joules at this point. So you multiply that out, that ends up being 3,600,000 joules. My guess is maybe that's why kilowatt hours stuck around as a unit, because it's just easier than reporting large numbers of joules. Okay. But you know what I would have done, like if I was making the standards back in the day, I would have just called it megajoules, because isn't this 3.6 megajoules? Like same thing. Like, so 1 kilowatt hour is the same thing as 3.6 megajoules. Okay, so we got kilowatt hours. You guys ever heard of calories? Calories? Ooh, that could represent some amount of energy, right? Now it turns out that 1 calorie, right? The definition of a calorie is the amount of energy that it takes to raise the temperature of 1 gram of water by 1 degree Celsius, okay, which has to do with the specific heat capacity of water. So 1 calorie ends up being 4.184 joules, right, equivalent. Right? So 4 joules about a calorie. Right? But you guys ever look on nutrition labels? Right? So you buy something in a box and says so many calories. Right? That's actually a different calorie than this. So that's 1 food calorie is a capital C calorie. Right? So that's like a food calorie. Right? And that's also called 1 kcal, 1,000 like little calories. Okay? So that's equivalent to 4,184 joules. Right? So if you see something on a box from the grocery store, it says it's like, this is 10 calories. You say, well, that's like 41,000 joules. Okay. You guys get that? All right. And one last way that I know you can quantify energy. I don't know, has anybody ever come across BTU, British Thermal Unit? So British Thermal Unit, BTU. I don't think I ever have, but if you guys ever see that out in the wild one day, it's approximately equal to 1,055 joules. Right, so there you go. Right, so there's different ways you can quantify energy. Of course, in this class, we really care about joules, right? So all the equations and stuff, we're just gonna be working in joules. Okay. Okay. But good to know, life stuff. All right, guys. All right, so now let's work towards this table right here. So we got ourselves a table. We did this one yesterday. Let's hit the second one here. I got a cannon firing a cannonball at some angle from ground level. Okay. Hey, this looks like a projectile, doesn't it? Right. I bet you could solve this with just past physics that you learned in this class a few weeks back. Right. Now, the question is the same for all these scenarios. It says, what is the speed of point B? You could ask other things too, but that's a pretty classic question. Okay? Do you guys think here, let's think the old way to do this. Right? The old way to do this is you have to know the blast speed of the cannonball, right? Which presumably that'd be given to you. Right? You'd also have to know the angle it was blasted at. But notice in the sub here, I just say SOMA angle. So I'm leaving it really generic. Right? In fact, I might not even tell you what the angle is. Right? Ooh, so already that's making this complicated. Then what you do is you break that into sine and cosine components, say, well, how fast is the ball going across the field? How fast is it going upward? But that fast upward immediately starts changing because gravity is pulling down. So you say, well, if it's risen some particular height, you can play off this third kinematic formula, say, here's the initial blast ball playing in the vertical direction. You say after some height change under Earth's gravity, it can slow down to some, right? And then now you're at point B, but now you have horizontal and vertical components, and you have to put it back together with the Pythagorean theorem. Right. So, that is a long, complicated process. I mean, you could do that, right? But that'd be a long, complicated process. But with this new method, right, conservation of energy, you guys see this is a much faster way to solve this, right? So what's in the system? I care about the cannonball. Okay, and guys, as the cannonball is flying through the air on a parabola path, what force is acting on it? Yeah,
Gravity.
gravitational force, which is provided by the Earth. Yeah. Right, so I have a cannonball Earth system. Now this is after it's been blasted from the cannon. So right, so I have this, and this is a closed system, right? So these two are pulling on each other. There's a force interaction. Right? That's the entire system. Right? So the energy at point A after it's left the barrel is all what kind of energy? Kinetic. 1/2 mv squared at point A, because look, it's down at ground level. So I'm going to say it's pretty much zero potential energy because it's at ground level, right? But it's moving really fast, moving as fast as it's ever going to move. So it definitely has kinetic. Okay. Now, by the time it rises to point B, well, it's definitely risen some height, so it's gained some kinetic, or sorry, some potential energy, I should say. Okay. That's like mgh at point B. Okay. Plus, it probably has some energy left over that's going into its motion. I bet it's moving there. Definitely if it's a projectile. So I bet it has some 1/2 mv squared left over. Right? In fact, that's what we're solving for, right? What's the speed at point B? Right? The only way it would not have any speed at point B is if the cannon was aimed straight upwards, and also this height happened to be the maximum height. Right? But that's a very special case, right? And this would happen to zero. Right? But in general, you can get something like that. Okay. Is that true? And then, because energy is conserved and this is a closed system, you could say, so a closed system, you could say the energy at point A is equal to the sum of the energy at point B. Okay? And at point A, it's just very simply kinetic energy, 1/2 mv squared versus point A. And at point B, well, it's an energy mix. Some of the energy went into lifting the cannonball, mgh at point B, and whatever was left over is going to translate into kinetic energy and give it a speed, 1/2 mv squared. Okay. So, like, can you solve for that VV? Right, guys that? You guys good so far? All right. Now, I'm going to solve this two different ways. I'm going to solve this in terms of variables. So, notice I haven't given you any numbers, right? I'm going to say like the mass is blah, blah, right? And then I'll go back and I'll give you guys mass of the cannonball and blast speed and the height and blah, blah, and we'll solve it in terms of numbers. So you guys get two perspectives on this. Okay? Right, so let's see, I see three terms. I'm going to do a bunch of algebra steps. And then the last step is going to say VB equals something, right? Right. Okay, so this is a really good skill to have. You guys seen this a number of times in this class. Hey, all three terms include what in them that can cancel out? Mass of the cannonball. Right. So once you know the blast speed, it turns out it doesn't matter what the mass of the cannonball is. You get the same answer regardless. Right. Maybe you would have predicted that because I mean that maybe has something to do possibly with Galileo motion, or the entire time we were doing projectiles, we never even cared about mass at that point in the class, right? Remember that mass is not part of these equations, so that might be a hint that mass would cancel out too. Or of course, we're not really focused on these equations. We're going to be doing conservation of energy, okay? So it's going to lead to the same outcome. Then let's see, I bet I could multiply everything by 2. So VB squared is equal to, I'm going to subtract this over 2. Right, and then multiply everything by 2, so that's VA squared minus 2GH. You're kind of squeezing 2 algebra steps there. Okay. But the last step is going to be square root both sides. So how fast it's going at point B is the square root of the blast speed squared minus 2 times the gravity field times the height change. Okay. Look at it, guys. Look at how fast that is. That's like 4 lines right there. Boom, 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 boom. Right? No like sine and cosine components and kinematic equations and Pythagorean theorem. No, there's none of that. Look, I just sliced through all that in like 4 steps, and you get straight to the answer. You see how fast that is? Right? Yeah, so that's like a way better way to solve it. Now, the information you lose is you lose directionality information. So I don't know like which way this is going. And it could be going on the way up, or it could be coming on the way down. Right? But this is the speed it would have. I can say speed. Right? So solve for V sub B. The answer is just what I boxed in right here. So I'm going to go, the speed at point B is the square root of the blast speed squared minus 2GH, the square root of all that. Okay. Ooh, that kind of looks like the Galileo question, doesn't it? Instead of the ball falling, it's going upwards. So maybe that's why we're subtracting 2GH instead of adding 2GH. Okay. And Okay, we got sort of like the square root of the velocity speed squared. Right. So do you guys can see how this would be consistent with that sort of? Yeah, I bet there's a connection there, right? Now I promised you guys that we'll do a numerical example. So let's do that. Okay, let me backtrack a few steps to the step right here. Okay, and let's feed some numbers into this. Here, I'll break out the pinky so you guys know I'm doing some numbers. Let's call the mass of the ball 1 kilogram, although you guys know that's not gonna matter anyway, but suppose this is my cannonball. Gonna cancel out in the end. Let's call the gravity field 10 meters per second squared. Will be on Earth. What else do I need? The height change in the blast speed. That's what you need. Right. Let's call the blast speed equal to about 100 meters per second. Okay, which is 200 something miles an hour. Right, so this thing is booking. And I'll have a height change of let's see how I want to do this. Let's have a height change of like 200 meters. How about that? Okay. Right. So with that information, we can figure out how fast the cannonball is going at the 200 meter high mark using this conservation of energy. Okay. And remember, this is regardless of the angle that the cannonball is blasted. Okay. So if the cannon blasts straight upwards, if it crosses 200 meter mark, it's going so fast. If it's blasting on an angle, see, as long as it gets up to that angle, if it barely like brushes up to the 200 meters, if that's like its maximum height, then whatever speed it's going at would be perfectly horizontal. But regardless, it's going to be going some speed. Right? Right. So let's feed these numbers into the setup. So I got 1/2 times the mass of the cannonball, I'll call 1 kilogram, and the blast speed is 100 meters per second. And square that, the speed. We'll say equals 1 kilogram times 10 meters per second squared times a height change of 200 meters. Right, and then whatever's left over is going to go 1/2 times 1 kilogram times the speed at point B being squared. Okay. Is that right? Okay, so energy accounting. So here I've got, let's see, 100 squares, 10,000 divided by 2. That's like 5,000 joules. Do you guys see 5,000 joules? Right. And see how many joules went into its height. Looks like 2,000 joules went into the height, and the rest is well, 1/2 mv squared. Okay, is that true? Which means that this whole kinetic energy bit represents how many joules? 3,000, right? You guys see 3,000? Okay, so we started off with 5,000, which means we always have 5,000 because it's a closed system. 2,000 joules went into lifting the cannonball. That means we have 3,000 joules left over. So this bit right here must be equal to 3,000 joules, right? And we use that to solve the rest of this, right? You guys get that? So let's do 1/2 times 1 kilogram times the speed at point B squared is equal to 3,000 joules. Okay. Multiply by 2, take the square root. So VB squared is 6,000 joules divided by kilograms, so meters squared per second squared. Okay. So last step, what's the square root of 6,000? So the speed at point B is 77.4 something, or so I'll call it 77 meters per second. There you go. Okay. So remember that I said this cannonball was blasted at like 100 meters per second. I just made up a number. Right? So as it's moving upwards, it's slowing down. And when it's gone 200 meters high, regardless of the angle that it went at, right, it's going this fast. Right? Now you could set up a projectile problem, go back to a few weeks back, break out like 10 sheets of paper, right, and do the whole like trigonometry components and kinematic blah 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 Pythagorean, right? And you would still get this answer. Right? It would just take a lot more time, a lot more work, and a lot more paper. Let's do this. Let's take this expression and run this check. Yeah, and then that'll be the last thing we do today. Right? So remember, I came up with like a general expression, right? Let's see if this actually works. Right? So I do. So it should be a giant square root. Do I have a? Here it is. Here it is. A little bit bigger. So it's a giant square root. The blast speed squared, so 100 meters per second being squared, minus 2 times the gravity field of 10 meters per second squared times the height change of 200 meters, right? Okay. Now, there's only one number that can pop up on my screen. And what does that number have to be? 77. It's like 77 and change, right? Let's see if it is. Moment of truth. 77. Bam. Meters per second. There you go. Right, so of course, in the peak geek, you guys see the actual energy accounting going through joules, right? But before that, we just solved in terms of variables. So we have an expression that can tell you the speed at any elevation for this cannonball. Okay. Right. And then, yeah, okay, so these other ones we're going to have to save for tomorrow. We have a couple of open systems coming up where there might be energy dissipated from the system. That's okay. We'll be able to handle those. Right. Yeah. So we're going to continue this adventure tomorrow. All right, who's got any questions today? Any questions today? All right.
For us, we're gonna say.